Regular expressions look like a cat walked across a keyboard, and yet they run the world. Every log pipeline, every input validator, every search and replace you've ever done in an editor, there's a regex in there somewhere. Here's the secret though. The entire regex language is about a dozen ideas. That's it. And if you watch each idea run against real data once, they stick forever. So that's the plan today. Real patterns, real text, real output, building from single characters all the way up to Lookaheads, and ending with a live demonstration of the famous regex that can freeze a server. By the end, you'll read these things like sentences. Our raw material for this whole video is text that actually exists in the wild, log lines. Here's a typical one. A date, a time, a level, and a message about a database timeout. And I'm importing our Python's regex module. Everything we learn transfers almost one-to-one to JavaScript, Java, Go, and your editor's search box. Idea number 1. \d means one digit. Any digit. Let's find all of them and print the first 8 so it fits on a line. Then idea number 2, the plus sign. Plus means one or more of the thing before me. So \d plus means whole runs of digits. And idea 3, curly braces for exact counts. \d 4 times, dash, d2 times, dash, d2 times. That's a date shape. And idea 4, the pipe, which means or, error, or warn, or info. Let's run all of these. Look at the progression. Single digits, chopped up. Then digit runs, 2026, 7, 3, all the numbers in the line as complete tokens. Then the date pattern plucks out exactly the date. And the alternation finds the log level. For patterns, and we've already extracted every interesting field in this line. Character class, quantifier, count, alternation. That's a third of the language already. And the family of character classes is tiny. \d, digits. \w, word characters, letters, digits, underscore. \s, white space. Capital versions mean the opposite. Capital D is anything that's not a digit. That means any character at all, and that one is dangerous. More on it soon. And square brackets let you build your own class. A to Z in brackets, or 0 to 9, or any literal set of characters you want. Same story with quantifiers. The whole family is 4 symbols. Plus means 1 or more. Star means 0 or more. Careful, that matches empty. Question mark means optional, 0 or 1. And the curly braces do exact counts and ranges, 3 exactly, 3 or more, or 2 to 5. Everything else in regex is built by combining these with the classes. That's why I said a dozen ideas. You've already met most of them. Before the fancy stuff, 30 seconds on how the engine actually works, because it explains every weird behavior you'll ever see. The engine walks your text left to right, trying to match the pattern starting at each position. At each step it asks, can the next piece of the pattern match the next piece of text? When a choice exists, like how many characters a plus should eat, the engine picks one option and remembers the alternatives. If it gets stuck later, it backtracks. It rewinds to the last choice point and tries the next option. Match greedily, hit a wall, back up, try again. Keep that word, backtracking, in your pocket. It's about to explain the greedy trap, and at the end of this video, it's going to explain something much darker. Now let's do real work. Parsing a whole log into structured data with groups. Here's a 4-line log. 2 errors, an info, and a warning. Real parsing means splitting each line into fields we can use from code. Parentheses in a regex do 2 jobs. They group things together, and they capture whatever matched inside. And Python has the nicest version of this, named groups. Question mark, capital P, and a name in angle brackets. So I'm building the full line pattern, piece by piece. A named date group, our date shape. A time group, a level group with the alternation. And a message group, .star, everything else to the end of the line. Also notice I'm using our e.compile and writing the pattern across multiple lines as adjacent strings. Long regexes don't have to be one line of noise. Build them from labeled pieces, and suddenly they're readable. Now the loop. For each line, match it and print the fields by name, like dictionary keys. And run. Look at that. Every line, decomposed. Level, time, message, cleanly separated, accessed by name, ready to filter or ship to a dashboard. This is the single most common professional use of regex, turning semi-structured text into actual data. And with named groups, the code reads like it was written by someone who likes you. Time for the trap that has claimed every regex user who ever lived. Greediness. Here's a line of HTML, a bold tag, an italic tag, some text, and I want to match the tags. Easy, right? A tag is an angle bracket, some stuff, another angle bracket. Less than, dot star, greater than. Let's also prepare the fixed candidates while we're here and compare all three. Run it and look at the first line. The obvious pattern matched one giant blob from the very first angle bracket all the way to the very last one, swallowing the bold text, the closing tag, the word, and the entire italic element. Everything. Why? Because dot star is greedy. Quantifiers eat as much as they possibly can and only give back the minimum needed for the rest of the pattern to succeed. Remember the backtracking engine. Dot star sprinted to the end of the string, then backed up just enough to find one final greater than sign. The match is technically correct and completely useless. Fix number 1, the question mark after the quantifier. Dot star question mark is lazy. It eats as little as possible, growing only when forced. For tags, matched perfectly. Fix number 2, and honestly the better one, the negated class. Less than, then any number of characters that are not a greater than sign, then greater than. Same for tags, but with zero backtracking drama, because it physically cannot cross a closing bracket. Say what you actually mean, and the engine doesn't have to guess. Next idea, position. Everything so far matches anywhere in the string. Anchors let you say where. Here's a list of words containing cat in various ways. Cat itself, catalog, concat, concatenate, and cat5. For experiments on them. Plain cat matches all 5 words. It just has to appear somewhere. Cat requires the match to start at the beginning, so concat and concatenate drop out. Cat $ requires beginning and end. The whole string must be exactly cat, one survivor. Anchors don't consume characters, they assert positions. And the last line is the underrated hero, \b, the word boundary. In a sentence full of cat-like words, \b cat \b found exactly the 2 standalone cats, ignoring the cat hiding inside concat. This is precisely the whole word option in your editor's search box. It's also the difference between replacing the variable count and mangling every account and counter in your codebase. Anchors and boundaries are what make regexes surgical instead of destructive. So far we've only found things. Regex is equally deadly at changing things. For real-world jobs, 1 file. Job 1, redacting secrets. Here's a config dump with a password and an API key in it, the kind of string that absolutely must not reach your logs. Our re.sub takes a pattern, a replacement, and the text. The pattern captures whether it's a password or an API key, matches the equals sign and the secret value, and the replacement writes back group 1. That's the \1 plus redacted. Job 2, cleaning whitespace chaos. Tabs, triple new lines, runs of spaces, all collapse to single spaces by replacing \s plus. Job 3, and this is the party trick, reformatting dates. Capture year, month, and day as 3 groups, then write them back in a different order, day.month.year. And job 4, splitting on multiple delimiters at once, commas, semicolons, or pipes, with optional spaces around them. Try doing that with a plain string split. And run. The secrets are gone, both of them, in one pass. The whitespace mess is now one clean sentence. The dates flipped from ISO format to European format, contents intact, structure rearranged, and the mixed delimiter lines split into 4 clean tokens. Every one of these is a one-liner that would otherwise be a loop with a pile of if statements. This file is basically a text processing toolbox you can keep. Quick pit stop before the power tools, flags, the little switches that change how a whole pattern behaves. Here's a 3-line report with error spelled 3 different ways. Capital E, lowercase, and all caps. And I'll search for error 3 times, with increasing amounts of help. And one more, the flag nobody uses and everybody should. Verbose mode, which lets you write a pattern across multiple lines, with whitespace and actual comments. Here's a phone number pattern where every piece is labeled, like real code. Watch the progression in the output. Plain, nothing. Lowercase error never appears at the start of the string. Ignorecase finds 1, the first line. And adding multiline finds both real errors, because multiline changes the meaning of from start of the whole string to start of every line. Exactly what you want on logs. And the verbose phone pattern parsed its number into named pieces while staying completely readable. Flags are one argument. Use them. Now the power tool, lookarounds. A lookahead checks what comes next without consuming it, without including it in the match. Here's a price list mixing dollar amounts and Turkish lira. I want just the dollar numbers, without the letters USD stuck to them. Digits, followed by $equals USD. The $equals part is the lookahead. It's a condition, not a capture. There's also the negative version, exclamation, meaning not followed by. Here, find me every log word, except login. And the flagship application of all of this, password rules. This pattern is on half the sign-up forms on the internet. 2 lookaheads and a length check. Somewhere ahead, there's a digit. Somewhere ahead, there's an uppercase letter. And the whole thing is at least 8 characters. Run it. The USD prices came out clean, for 50 and 320, no currency letters attached, and no lira amounts. The negative lookahead kept logout, log, and logging, but skipped login. And the password rule. Weak pass rejected, no digit, no uppercase. Strong pass with a 0 and capitals, accepted. Short, rejected on length. Notice the trick that makes this work. Both lookaheads start checking from the same position, the start of the string. They stack, like a checklist, because neither one consumes anything. There are loop behinds too, less than, equals, checking what comes before a position, same idea in the other direction. With lookarounds, your patterns stop being just find this shape and become find this shape in this context. That's the difference between a Regex user and a Regex craftsman. And now, the finale I promised. The Regex that can take down a server. I want to show you what happens when backtracking goes nuclear. Here's an innocent-looking pattern. Open paren, a plus, close paren, plus, $. 1 or more runs of 1 or more A's, filling the whole string. Redundant, but harmless looking. And I'll feed it strings of A's, with an exclamation mark at the end, so the match is doomed to fail. 20 A's, then 22, up to 28, timing each attempt. Before I run it, think about what the engine has to do. The string can't match, there's an exclamation mark at the end. But to prove that, the engine tries every possible way of splitting the A's into groups of runs. 20 A's as 1 run of 20, as 20 runs of 1, as every combination in between. That's an exponential number of splits. Each added character doubles the work. Let's watch it happen. 20 characters, 47 milliseconds. 22, 200 milliseconds. 24, almost a second. 26, over 3 seconds. And 28 characters, 26 seconds. 26 seconds. To fail a match on a 28-character string. This is catastrophic backtracking, and its weaponized form is called a re.sub, a regular expression denial of service. It's not theoretical. In 2019, Cloudflare, the company that carries a huge slice of the world's web traffic, went down globally for half an hour because of one regex with exactly this shape in their firewall rules. One pattern, CPS pinned at 100%, worldwide outage. The defenses are simple. Never nest quantifiers over overlapping choices. That's the whole disease. Prefer explicit character classes, like our negated bracket trick. They give the engine nothing to guess about. Treat regexes that run on user input as code that needs review and timeouts. And know that some engines, like Go's RE2 and Rust's Regex crate, guarantee linear time by construction at the cost of dropping back references and lookarounds. Engineering trade-offs, all the way down. Let's fold the whole language back into your pocket. Character classes and quantifiers describe shapes. Groups capture the pieces, and named groups keep you sane. Greedy quantifiers eat everything, so reach for lazy versions or negated classes. Anchors and word boundaries pin the position. Sub and split turn patterns into transformations. Lookarounds add context without consuming it. And under it all runs a backtracking engine that is powerful, literal, and occasionally explosive, so patterns on user input deserve the same paranoia as any other code. That's genuinely the whole language. A dozen ideas, and you've now seen every one of them run. Next time a regex appears in a code review, you won't skim past it, you'll read it, and you might be the one who spots the nested quantifier before it takes the site down. If this demystified regex for you, a like really helps the channel, and subscribe for more deep dives. Next up, we're writing a programming language interpreter from scratch that actually runs code. See you there.